It's my pleasure to invite you all for this last talk in this FC Kohli series. It's also my pleasure to introduce Uma Girish. Uma Girish is a PhD student at Princeton University. She's working for her PhD with Professor Raz. So she is a former student. She graduated with a BSc in Mathematics and Computer Science at CMI. And in 2016, then she went to do her master's here. But for her thesis, she worked with Professor Piyush Srivastava at the Tata Institute of Fundamental Research in Mumbai. And she also was mentored by Professor Jayakumar Radhakrishnan there. Uma's primary interests are computational complexity and algorithms with a focused interest in quantum computing and Boolean function analysis. Yeah, Uma, the floor is yours.
Yeah, thank you, KV. Also, thanks for inviting me. I'm very happy to be back at CMI to give a talk. So I hope you can see my screen. I will be telling you about the problem of eliminating intermediate measurements in quantum algorithms. This talk will be based on a series of works with Raz and Zhan, and by another work by these authors, Bill Fefferman and Zachary Remscrim. So here are the two results I'm going to be talking about. So these results are about how to defer intermediate measurements for quantum algorithms. Given a quantum algorithm of time t and space s with unitary operators and intermediate measurements, how can you simulate it by an algorithm with only unitary operators and without intermediate measurements? The first result we'll see will show a simulation that runs in time t times 2 to the order s and space s plus log t. So this was proved independently by Fefferman and Remscrim and myself, Ron, and Wei. This result also has connections to the problem of contraction matrix powering. The second result shows a simulation that runs in time t poly s and space s log t. This is a result by myself and Ran Raz, and this result has connections to pseudo-random generators for quantum algorithms. So this is a quick preview of my results, and this result by Fefferman and Remscrim. And in the rest of this talk, I'll go on to give more detail and background for these results. So my plan for the talk is to spend the next 10 minutes talking about quantum algorithms and going over what they can do, what they can't do. And the next 20 minutes or so, I will describe these results in more detail. And in the last 15 to 20 minutes, I'll try to describe some of the ideas involved in the proofs of these. Okay, so let's start with what are quantum algorithms. So for those of you familiar with complexity theory, there are two ways to define space-bounded computation. One is to define this object called Turing machine and talk about how much space and time is used by a Turing machine. Another way to define space-bounded computation is to make use of uniform families of space-bounded circuits. In the classical case, these are equivalent ways of looking at the same object. In the quantum case, defining a notion of quantum Turing machine is surprisingly intricate. So we're going to just work with the definition 2. And in certain cases, we know that these two are identical, although formal analysis has not been done. For simplicity, we're just going to work with the second definition. Okay, so now let me define what a space-bounded circuit is. So for us, quantum algorithms of space s and time t are basically quantum circuits with s qubits and t operators. So you have s qubits, all initialized to the ket0 state, and you have a sequence of t quantum operators that are applied on this circuit. So for now, just think of quantum operator as some building block for a quantum circuit. So here is an example of a quantum circuit on 5 qubits with 10 operators. Now let me describe what these operators are. So as I said, operators are building blocks of quantum circuits. The building blocks that are available to us are these 4 operators. You have the Hadamard gate, the Toffoli operator, the measurement operator, and the reset operator. So let's talk about these in more detail. First, let's look at Hadamard and Toffoli. So these are unitary operators. So recall from Ronald's lecture that given any bunch of qubits, the state on that of those qubits can be represented by a unit vector typically, and quantum evolutions can be described as unitary transformations. So in that framework, these two operators, Hadamard and Toffoli, are unitary transformations. The Hadamard acts on 1 qubit, whereas the Toffoli acts on 3 qubits, and this is the action. So for us, it's not going to be important what exactly these transformations are. What's interesting about these two operators is that any unitary you want to implement, you could approximate by a combination of these two operators. So these two operators collectively kind of describe all possible unitary operators that you could hope to implement. So now let's talk about the other two operators, measurement and reset operators. So first of all, these are not unitary operators. So typically we're used to seeing quantum operators as unitary, but the most general formulation requires you to have more general operators. So let's look at the first such operator. It's the measurement operator. So what does a measurement do? Measurement basically allows you to extract meaningful information from the quantum circuit. So you have a quantum circuit and you have a quantum state that is produced at the very end of the computation. This state is a superposition state over basis states. How do you get something meaningful from this state? You get something meaningful by measuring it. And in this talk, we'll be focusing on measurements in the basis state. So what does that do? In particular, we're going to look at measurement of a single qubit. So what that does is it takes a qubit in the state alpha ket 0 plus beta ket 1. This is some superposition of 0 and 1. When you measure this qubit, you're going to get a probabilistic outcome. This outcome is going to be 0 with certain probability and 1 with certain probability. So it's going to be 0 with probability mod alpha square and 1 with probability mod beta square. Since this is a unit vector, this is a well-defined, you're going to get only one of these outcomes. And when you observe the outcome 0, the state becomes ket 0. And when you measure the outcome 1, the state becomes ket 1. So this is the measurement operator. One important remark about this operator is that this is not unitary. In the sense, if you take a qubit and measure it, you cannot undo the measurement and recover the state of the qubit before the measurement. So after you do a measurement, the qubit behaves as though it was 0 with probability alpha square and 1 with probability mod beta square. This is different from the state that is a superposition of 0 and 1 with coefficients alpha and beta. So this state, which is 0 with some probability and 1 with some other probability, is different from the superposition of 0 and 1. So yeah, this, to stress again, this operator is not unitary and it's not a reversible operation. You cannot recover the state of the qubit as it was before measurement. So effectively, a measurement kind of collapses a quantum state. That's what it does. Finally, I want to talk about the reset operator. Now, this is an obviously non-unitary operator. What it does is takes a qubit in an arbitrary state and replaces it by a fresh qubit in the ket 0 state. So the way to think of this is as though somebody had removed this qubit from the system and introduced a new qubit in the 0 state that is unentangled with the rest of the qubits. So the reason why we include this operation that is so obviously non-unitary is because when we talk about space-bounded algorithms, they often want to reuse their space. So this is easy for a classical bounded space algorithm to do. If you have a memory at a certain time, you can very easily erase that memory, so to speak. But for quantum algorithms, typically we don't allow these kind of operations. Typically we only allow unitary operations. And so the problem of reusing memory becomes more important. So in particular, it's not even clear that quantum space-bounded algorithms can simulate classical space-bounded algorithms just because they're not able to erase the memory. So to define the most general model of quantum algorithm, which we would ideally want to be more powerful than the classical model, we include this reset operator. So another way of thinking of algorithms with reset operators is to think of them as algorithms with both quantum and classical memory. So on the quantum memory, you can do commonly thought of quantum operations like unitaries and measurements. And on the classical part, you can do classical operations like erasing qubits. And there is some limited interaction between the quantum and classical part. It turns out that this reset operation is quite powerful. In the sense, using a reset operation and a Toffoli, you can actually simulate the measurement of a qubit. So this reset operation is really powerful. And the problem of eliminating intermediate measurements becomes trivial if you have this reset operator. So we are going to be interested in the case when you don't have this reset operator. So going back to our question of what is a quantum algorithm of space S time t?
Uma, hi, can I ask a question?
Yeah, sure.
Yeah, so the reset is different from measurement X only for ket 1, right? I mean, otherwise you can do enough number of measurements, and once you get the value corresponding to ket 0, you stop, and that is like a reset to 0, right? So except if you are in ket 1, it's only for ket 1 that it's a different operator. Is that correct? Or?
So yeah, the behavior of these two operations are same except on the state ket 1.
Yeah.
But the problem is you can't. So once you measure a qubit, you can't say if it is 1, do something, if it is 0, do something else, on that qubit itself.
Mm-hmm. I see.
So yeah, does that answer your question?
Yeah. Okay, thanks.
Yeah. Sorry, I should have said, but feel free to stop and ask questions. Okay, so this was just a broad discussion of what all goes into defining quantum algorithms. But even if you have not followed the discussion, now is a good time to join back. So what's a quantum algorithm of space S and time t? For us, basically, it's a quantum circuit with S qubits that are initialized to the ket 0 state and T operators which are applied. What kind of operators are allowed? We're going to allow only Hadamard's, Toffoli's, and measurements. Sometimes we'll only allow Hadamard's and Toffoli's, that is unitary operators, and this is what we call the unitary model. Suppose we allow intermediate measurements, that is measurements during computation, we call this the unital model. So there are two comments I want to make here. First is, how does the input and output enter the picture? So typically algorithms need an input and they produce an output. So how does that enter this picture? Well, the input is what decides the quantum circuit. So we require that there is a classical log space algorithm which, given an input X, produces the description of this quantum circuit. So this quantum circuit is not magically produced by some computationally unbounded person, but it's actually describable by a small classical log space algorithm. Secondly, what is the output of such a circuit? So the output needs to be classical. So what we do is at the very end of the computation, at the very end of the circuit, we measure some of the qubits and declare the measurement outcome as the output of the circuit. Note that this measurement is only done at the very end before declaring the output. So this is how the input and output enters the picture. But for the rest of this talk, you can just forget this input-output business and just think of a quantum circuit that somebody has given to you with S qubits and T operators. The second comment I want to make is that what happens to these measurement outcomes? So let's say you measure a qubit, you get an outcome. Are you allowed to store that outcome in this unital model? So our model of unital computation allows us to store measurement outcomes, but every time you store a measurement outcome, you need to pay for the space required to store it. So in particular, if you're making S measurements, you cannot store more than S measurements at a time. So any questions about the model so far?
Uma, I had one more question, sorry. So when you say the T operators, I mean, if I take one of the unitaries, I mean, if you have a one parameter family of unitary, usually we would think it's associated to continuous time, right? Like if you somehow you have discrete number of time steps, and even a given unitary is associated to a given operation at given time. Is that the right way to understand this? Or
sorry, could you say that again? The last part?
Yeah, so you have T operators. I mean, like you have say like T number of operators, right? Even the unitary is one of these operators. Is that correct?
Yes, yes.
But usually unitaries we associate to continuous time operation, right? I mean, you see what I'm saying? Like you just you have a one parameter family of unitaries, then it's evolving a state in continuous time. So I don't know. It's not a very precise question, but somehow the fact that you have discrete time steps and you still have unitaries.
Yeah, I mean, it's not like e to the IHT or something. It's just like
but it's allowed, right? For you, it's allowed, right? The IHT is allowed for you, right? Or it's not allowed.
So actually, right now I'm only talking about discrete time.
Okay. So you not all unitaries, only discrete unitaries.
Discrete, and also like at time 1 you can apply Hadamard, time 2 you can apply something else, and so on. Yeah. So
okay, thank you.
Discrete.
I had another question. When you say that when you store the measurement outcomes, why do we limit that? Because the measurement outcome should be classical and that shouldn't be a problem, right? Why are we limiting?
Because we want classical memory also to be small. So we are not considering quantum algorithms with limited quantum memory but unlimited classical memory. We are considering algorithms where both the quantum and classical memory are limited.
Okay, so space S then means that you have S qubits and S bits.
Yeah, you can think of it like that.
Okay.
Exactly.
Okay.
Because once you allow like a lot of classical memory, you can do a lot more powerful stuff. This is more complicated than, yeah. Okay, so if there are no other questions, I'll now move on to the main problem of interest. So this is the problem of eliminating intermediate measurements. The basic question is, now that I've introduced these two models, the question is, are these two models different? So given a quantum algorithm with intermediate measurements, can we simulate it by a quantum algorithm without intermediate measurements? Or are quantum algorithms with intermediate measurements more powerful than algorithms that cannot do intermediate measurements? Do intermediate measurements give power to quantum computation? This is the question we're interested in studying. This is a really fundamental question in quantum computing. There are many settings in which it's desirable to have unitary algorithms without intermediate measurements. So this question is interesting with regards to reversibility of computation. Since measurements are not reversible operations, we're asking, can we simulate this irreversible operation of doing a measurement by reversible operations like Hadamard and Toffoli's? So one reason why such a result might be interesting is because we know a lot of procedures for reversible algorithms. For example, space and time efficient error reduction is known for reversible algorithms, but not for irreversible algorithms. It turns out this question also has connections to pseudo-randomness, which I will describe later. So this is the main problem. What do we know about this problem? A very basic principle in quantum computing is the principle of deferred measurements. So this says that instead of measuring a qubit, you can copy it onto a fresh qubit, copy so to speak, and ignore this fresh qubit for the rest of the computation. So instead of measuring this qubit, you apply a control knot, which is a special case of Toffoli. You apply this control knot onto a fresh qubit and don't touch this fresh qubit for the rest of this computation.
So
the principle of deferred measurement.
If you have any intermediate measurement at all, you will, in general, generically, you will produce mixtures, right?
Yes.
So, and that, so how are you, and whereas if you don't have any intermediate measurement, you will end up with a pure state at the end. So how are you going to eliminate, I mean, it seems sort of impossible to have a procedure to eliminate.
Right, but you can think of a purification of a mixed state. So you can think of embedding this mixed state as a pure state in a few larger dimensions.
Okay.
That's exactly what we're aiming at.
Okay. Thank you. Go ahead.
Okay, so yeah, so this is the principle of deferred measurements. It's saying that if you do this operation on the qubit, you can treat it as though it had been measured. So this implies that for time t spaces algorithms with intermediate measurements, you can defer the intermediate measurements in time t and space s plus t. So why space s plus t? To defer each of these intermediate measurements, you need a fresh qubit, and the algorithm could perform potentially t intermediate measurements. So the final algorithm will require space s plus t in the worst case. So it's often the case that s is much smaller than t. So think of the setting when s is polylog t. In this case, the blow-up in space is exponential. So the principle of deferred measurements, as is commonly stated, is space inefficient. So one can ask, is there a version of the principle of deferred measurements that is space efficient? Can we defer intermediate measurements in a space efficient manner? This was an open question. Until last year, it was resolved by these two independent works that indeed there is a space-efficient elimination of intermediate measurements. So this is the first result that I described in the first slide. This says that for time t spaces algorithms, you can defer intermediate measurements in space s plus log t and time poly t 2 to the s. So this is the main theorem. And at the heart of this result is the following result. So this paper, these two papers also show a unitary quantum algorithm for powering certain kinds of matrices. So the matrix powering problem is the following. You're given a contraction matrix A, that is a matrix with spectral norm at most 1, and you're asked to approximate the entries of the powers of this matrix. More precisely, you're given a parameter T, indices I and J, and some error parameter epsilon, and you want to approximate the ijth entry of A to the power T up to epsilon additive error. These two works show that this problem can be solved in unitary quantum log space. So the very heart of the simulation result is a algorithmic result. That is, you can solve this matrix powering problem in unitary quantum log space. And in fact, this problem is in some sense complete for quantum log space. So this is the first result.
What is quantum log space?
Yeah, good question. So I should have defined it, but log space is S is logarithmic in n and T is polynomial in n, where n is the input length. So yeah. So it's like classical log space, but yeah, it's quantum.
Okay, thank you.
So one comment about these two works. So the result of GRZ shows exactly this. The result of FR21 shows something quite stronger. So they show that even reset operations can be eliminated in similar time and space. So in particular, it implies that measurements can be removed in this much time and space. And their result also relies on showing that a certain matrix powering problem is in unitary log space, but this problem is more general than contraction matrix powering. So this problem is where you have a matrix, all of whose powers have some bounded norm, bounded by some polynomial in n. So they show that such kind of matrices can also be approximately powered in unitary quantum log space. So time permitting, I will describe the connection between this simulating quantum algorithms and the seemingly unrelated problem of contraction matrix powering. For now, let's just look at an example of this result in the log space setting. So by log space, again, I mean S is logarithmic in n and T is polynomial in n. So n is the length of the input, or you can just think of T as something that's exponential in S. So in this setting, poly t to the s is polynomial in n, and s plus log t is also logarithmic in n. So this is saying that if you look at log space quantum algorithms, they don't need intermediate measurements. So this is a powerful result. Let's see how it affects.
Sorry, just to clarify, in the top theorem, reset was allowed, right? It was included in this theorem.
So when we say quantum algorithm in this talk, we're not going to allow reset.
Okay. Only unitaries now. In this
Only
theorem.
unitaries now.
I see. Okay. Thanks.
Yeah, because if you're just talking about eliminating intermediate measurement, once you have a reset operation, it's trivial.
Right. Okay, that's what you said.
Yeah. The other result I was talking about, this Fefferman and Remscrim, they show how to even remove the reset operation. So they have the same result, but instead of intermediate operation, you have reset operations.
Okay.
That's what I wanted to comment. But yeah. Okay, so let's look at the application of this result to the log space computational world. So this is the picture of log space computation. Here you have classical deterministic log space is contained in randomized log space. It can also be shown that classical deterministic log space is contained in quantum log space with only unitary operators. And of course, this is contained in the corresponding quantum class with unitary operators and intermediate measurements. And the strongest class is unitaries plus intermediate measurements plus reset operations. So the results of these two works can be summarized as follows. So GRZ21 shows that these two computational classes are equal, and FR21 shows that these two computational classes are equal. So really all these three objects are the same object, quantum log space with only unitary operators. One interesting consequence of this result is that randomized log space can be simulated by quantum log space with only unitary operators. Surprisingly, this result was not known before. So I think that's a really interesting consequence of the fact that you can eliminate these reset operations and intermediate measurements. So any questions about these results?
Uma, maybe I can ask one question. So your theorem one, is it effectively telling you that like doing measurement is same as doing like a sequence of unitaries in this case, in the case of quantum circuits? I mean, is that a right way to understand the theorem? Or I mean, the reason I'm asking is because in physics, measurement is something related to this. You need a classical apparatus, and you cannot sort of mimic it with unitaries, as quantum unitaries, right? So it seems like a profound result in that sense, from that perspective.
Yeah, it is interesting on the, so one way to make this more clear why such a thing should be true is if you take any quantum log space algorithm with unitary operators and intermediate measurements, you just look at the compound operator, like you collect all these operators and see what quantum operator they implement. We know that whatever quantum operator they can implement can be kind of embedded as a unitary operator over slightly larger dimensions. We know that such a result anyway holds, but the question here is how do you find such a, how do you find this operator and embed it as a unitary? And how do you produce this? How do you express that unitary as a sequence of Hadamard's and Toffoli's?
Yes.
So, I mean, we know in some sense that every 2 to the s by 2 to the s operator, quantum operation can be thought of as a unitary operation over 2 to the s, 2 to the 2s by 2 to the 2s. And then at the very end applying some measurement and ignoring some qubits.
Okay, maybe it's a finite dimensional Hilbert space. So the usual issue with measurement, which is about infinite dimensional Hilbert space, is not. I mean, it's a profound result from that perspective, from the perspective of quantum mechanics. But maybe I'll ask you later after the talk.
Yeah. Okay. Yeah. It's really interesting that computationally that you can do this computationally efficiently. Maybe that's the more interesting aspect of this result.
So what was known before about what could be simulated in quantum? This is quantum log space, but what was known before this actually about what kind of algorithm?
Yeah, interestingly, like this problem wasn't studied before. For just eliminating intermediate measurements was not studied before.
But in complexity theory, I mean, what the containment sort of known?
So you mean what is this picture before these works?
Yeah, no, because you said randomized log space, because we know some containments of randomized log space in the standard complexity classes, but what was the connections between, so this is of course quantum log space, quantum P, I suppose people had studied.
Oh, there we know how that randomized P is contained in quantum P just because you have a lot of space.
Correct. Okay. Oh, so this is interesting actually. Yeah. Okay.
Yeah. The whole problem of eliminating intermediate measurements is particularly magnified in the small space setting because you cannot easily remove measurements in small space. So that's where this. Yeah. Interestingly, pretty much nothing was known about this question before these two works.
Okay. Nice. Yeah. Thanks.
Yeah. So any more questions about this result? Okay. So let's move on to the second result. And the second result is based on the following drawback of this result. So the theorem I just showed is about how to defer intermediate measurements in space S plus log t. But this procedure takes time poly t 2 to the s. So originally we had a principle of deferred measurements that was only really effective in the large space regime. This result is only really effective in the small space regime. So in the setting when 2 to the s is at most t, or in particular for log space algorithms, the runtime continues to be polynomial. But when s is even slightly larger than logarithmic in t, then this becomes quasi-polynomial. So the best simulations of algorithms with measurements by algorithms without measurements required either time 2 to the s or space t. So one can ask, can we do better? Can we defer intermediate measurements in time better than t to the s and space better than t simultaneously? Can we defer intermediate measurements in a space and time efficient manner? And this brings us to the second result that I mentioned in the first slide. So this is a time and space efficient elimination of intermediate measurements. So this result says that given a quantum algorithm of time t and space s with intermediate measurements, you can simulate it without intermediate measurements in time t poly s and space s log t. So s times log t. So this is a time and space efficient simulation. For example, it implies that quantum algorithms of polylogarithmic space and polynomial time don't require intermediate measurements. The proof of this result relies on an interesting connection to pseudo-random generators, and that is one of the other contributions of this work. So let me describe this connection. The connection is in the following powerful observation that intermediate measurements and randomness are equivalent. Let's see what that means. First, intermediate measurements can be used to generate randomness. Imagine you have a qubit in the state ket 0, apply a Hadamard and then measure it. The Hadamard is going to produce a uniform superposition over 0 and 1. And when you do a measurement, you're going to get 0 with probability half and 1 with probability half. To generate more random bits, you can take the same qubit and apply a Hadamard and measurement again. You're again going to get a uniformly random bit that is independent of the first random bit that you obtain. So intermediate measurements can be used to generate an arbitrary long sequence of uniform independent random bits. Interestingly, the other direction also holds. So randomness can be used to simulate intermediate measurements. So we show that instead of measuring a qubit, you can apply a controlled unitary on that qubit, where the control is on a uniformly random bit. So imagine you had a qubit that was in the state 0 with probability half and 1 with probability half. controlled on that qubit if you apply a measurement, if you apply unitary U1 on this qubit, it is equivalent to measuring this qubit. The proof of this is quite simple. It just involves writing out the basis states and seeing what the action of the basis of these two operators is on the basis states and checking that they're equal. So this whole, these two slides imply that intermediate measurements and randomness are equivalent. Therefore, given any quantum algorithm with intermediate measurements, you can write down an equivalent quantum algorithm without intermediate measurements, but which has access to a sequence of uniformly random bits. So the problem of eliminating intermediate measurements is equivalent to the problem of removing random bits, or in other words, the problem of de-randomization. The idea is that you take this equivalent randomized quantum algorithm, so to speak. So you take this quantum algorithm, which reads classical random bits. And the idea is to replace these uniformly random bits by pseudo-random bits. That is, replace the random bits used by this quantum algorithm by pseudo-random bits. By this, I mean random bits that actually contain very few bits of true randomness, and the rest of the bits are a function of these few random bits. So this naturally leads us to the concept of a pseudo-random generator, which I'm going to describe in the next slide. So what's a pseudo-random generator? It's a function that stretches a few random bits to produce a large number of random bits. And the property we want of a pseudo-random generator is the following. In the ideal case, so let's fix an algorithm f of time t and space s. In the ideal case, you're giving this algorithm uniformly random bits over a large universe. You're giving it capital T uniformly random bits. In the non-ideal case, you have little t random bits. You're stretching it using the pseudo-random generator and then feeding the output to the algorithm f. The property we want of a pseudo-random generator is that the behavior of these algorithms in these two different cases is nearly identical. In other words, we want to mimic the behavior of the algorithm on a large number of random bits by using just a few number of random bits and applying a generator to those few random bits. So this is what a pseudo-random generator does. A little more formally, what it does is that the property that we want is that the final state of the algorithm, when the random bits are drawn from the output of the pseudo-random generator on a uniformly random input, this final state is close to the final state of the algorithm when the random bits are drawn uniformly and independently. So this epsilon indistinguishable just means that the difference in the norm of the final state in these two cases is at most epsilon. So norm is the usual distance between quantum states norm. So now I'm ready to state the second contribution of this work, which is at the heart of the result. So the work I mentioned before, this shows that a variant of the INW generator is actually a PRG for quantum algorithms of time t and space s, which read classical random bits. So the INW generator, the Impaglia-Sonis-Wigderson generator, is a famous classical pseudo-random generator. It works for time t space s classical algorithms and has seed length S.logT. This result shows that a variant of this pseudo-random generator actually works for quantum algorithms of space s time t, which read classical random bits. This is what underlies the simulation of algorithms with measurements by algorithms without measurements. One comment here is that this pseudo-random generator works even for quantum algorithms that can reset qubits. But the reason we don't state it is because the main application is to eliminate intermediate measurements. So, but just a remark that this holds in more generality than I stated. Let me talk a little bit more about PRGs for quantum algorithms. So first, people have not really studied pseudo-random generators for quantum algorithms that read classical random bits. presumably because quantum algorithms can generate perfect randomness, as I described before. But this relies on the ability of the algorithm to perform intermediate measurements. So we think one setting that PRGs might be interesting in is the setting when either the algorithm cannot perform intermediate measurements or it cannot be relied to perform intermediate measurements as it's supposed to do. So in settings, when you have a protocol where you're asking the quantum algorithm to toss random coins or apply intermediate measurements, but you cannot be certain that the quantum algorithm is doing what it's supposed to do, nor do you have the ability to toss those random bits yourself, then PRGs might find applications in this setting. So another reason we think PRGs might be interesting is that they give an example of this distinguishability task that you can show small space quantum algorithms cannot solve. So just the problem of distinguishing a random string, a truly random string from a pseudo-random string, is something that small space quantum algorithms cannot solve.
Mm-hmm.
So we think PRGs might be interesting from other perspectives, but of course our main application for PRGs for quantum algorithms that read randomness is in this problem of eliminating intermediate measurements. So any questions about the results so far?
So what about distinguishing when I'm allowed, suppose you don't restrict the space, but you, does that make sense? I suppose what is known, and if I were to just look at time there? Is something known? I mean, I'm just...
So for large space algorithms, since measurements are easy to eliminate, I feel like something like this could be true, but I'm not sure. Pseudo-random generator is asking for something more. So yeah, I don't know. Yeah, so if there are no more questions about the results, in the next 10 minutes or so, I'll try to describe some of the ideas behind the proofs of these results. Let me start by going back to the first result, which is a space-efficient way to differ intermediate measurements. So there I said that the heart of this result is in some contraction matrix powering algorithm. So let me describe that connection a bit more. So in the next 5 minutes, I'm going to show what is the connection between eliminating intermediate measurements and contraction matrix powering. The connection is quite simple, actually. So first, let's look at an algorithm with only unitary operators. So you have this quantum circuit. The initial state is the all zero state. And you're applying T unitary operators. And each of these operators is a 2 to the S by 2 to the S unitary matrix. See, the initial state of this circuit, of these qubits, is just the all zero state. The final state after applying all these operators is the following state. So if you remember from Ronald's lecture, this is how the quantum state evolves under a unitary operator. So the final state can be described as ut times ut minus 1 up to u1 acting on v0. So already you have some kind of matrix multiplication going on here. So v0 is just this fixed unit vector where the first coordinate is 1. And here you have a product of T unitary matrices of size 2 to the S by 2 to the S. So if somebody gave you a unitary matrix multiplication algorithm, then you can use that algorithm to estimate the entries of this final state and in some sense recover this final state. So now what happens when you have measurement operators? It turns out that you can do a similar calculation, but it's slightly more complicated in the sense you're matrices are now 2 to the 2s by 2 to the 2s, even though you only have s qubits. You have T matrices as before. Okay, sorry, this should be 2T because you're applying a unitary and a measurement. This is a product of 2T contraction matrices of size 2 to the 2s by 2 to the 2s. So for these unitary operators, the corresponding matrix you get is actually unitary. It's these measurement operators that introduce matrices whose spectral norm is less than 1. So this matrix M, which is the measurement of the first qubit, is a block diagonal matrix where some of the block diagonal entries are 1 and some of them are 0. So this is what you get. If you're familiar with the density matrix formulation, then this is essentially writing out the density matrices as a product of the transformations acting on the initial density matrix. So here you can think of rho 0 and rho t as taking the density matrix corresponding to the quantum state and writing all the rows one after the other, or all the columns one after the other. So
the reason why the size blows up, what is?
Yeah, so yeah, the main point is that if you want to understand the evolution of a system that is not unitary, it doesn't suffice to deal with unit vectors in 2 to the dimension. So if you have s qubits, typically you say you need 2 to the s dimensions to describe a unit vector in that, but this is only for pure states. So if you apply measurement on those qubits, then you need to use matrices. You need to use 2 to the s by 2 to the s matrices to describe the quantum state. Unit vectors are not enough.
Okay.
Is
And
it
if you write down, yeah.
Is it the same measurement that you repeat, or are these all?
So this is just an example.
Okay.
But any measurement on, so we're only considering single qubit measurements, and any of those can be written in this form.
Okay.
So Uma, when you perform the measurement, I mean, it should also affect the state of the measuring apparatus, right? So that's included in this larger embedding somehow. Is that? I mean, your measurement is being read by an apparatus, right? And that Hilbert space of that apparatus is somehow, is that why this larger embedding is necessary?
Not really. Actually, this is what allows us to ignore the observer. So ideally, you would want to, take the system plus the observer and evolve everything in this entangled pure state. But yes, this density matrix formulation is what allows us to ignore the observer. So
when you say you perform measurement, it's being read on an apparatus, state of an apparatus, right? I mean, maybe I'm not seeing it in the.
Yeah.
Isn't it that once you make a measurement, this instrument is no longer used, right? For the next measurement, you use another instrument.
Yeah, in some sense, it's not like you can store the measurement. You can't take out the measurement outcome and do some complicated things with it. Literally, the only purpose of this apparatus is to collapse the quantum state.
Okay. You're not reading the measurement. That's not your purpose. You don't care.
Yeah, because we want to. You can technically read the measurement, by doing a control knot, but you're going to have to pay in terms of the price.
Okay. Thank you.
Yeah. So literally, the only way this measurement behaves is it collapses the quantum state. Yeah. Okay, so this is the connection between matrix multiplication and eliminating intermediate measurements. In the next 5 minutes or so, I'll describe some of the ideas behind the algorithm for contraction matrix powering. So just to recap what happened here, we said that the final state of the quantum algorithm can be written as a product of T contraction matrices of size 2 to the s by 2 to the s. So this is for algorithms with unitary operators and intermediate measurements. So if you had an algorithm to multiply contraction matrices, this is equivalent to an algorithm to power contraction matrices. Then you can estimate the entries of the final state and you can sort of recover the final state of the quantum algorithm. One comment I want to make is that if your algorithm also had reset operations, a similar result holds, but these matrices are no longer contraction matrices. They're just matrices, all of whose powers have bounded norm. So all the powers have norm bounded by polynomial in n, but in this case, exponential in s. Yeah, I was thinking of log space, but here you have exponential in s. Okay, so let's talk more about how to multiply contraction matrices or how to power contraction matrices. Yeah, so how do we solve contraction matrix powering in unitary quantum log space? So I just want to give you a flavor of the kind of ideas that are involved. So it's a careful combination of ideas that have already been developed, but you need to make some modifications along the way. So the first step is you're given this contraction matrix. The idea is to embed it inside some quantum circuit. So this operator A has spectral norm at most 1. So you can embed it inside a unitary operator. So imagine putting some entries here. So we call these stars, so that this whole matrix is unitary. Such a thing can be done. And not only that, you can efficiently construct a small quantum circuit that actually embeds this operator A, this contraction matrix. So this uses some powerful techniques. If you remember from Ronald's talk, he talked about Hamiltonian simulation. So in this problem, you're given a Hermitian matrix, either local Hermitian or you're just given the whole Hermitian matrix, and you need to implement e to the power IH. This is a unitary matrix. So this problem has been studied, and there are many results on this problem. In particular, we're going to use the log space version of this. So Amnon Tashma showed that given an n by n Hermitian matrix, you can, in quantum unitary log space, you can efficiently implement e to the IH, approximately. So we use this procedure to build this embedding. So this is our first step. Given a contraction matrix, we embed it inside a quantum circuit. That is, if you look at the unitary operator that is implemented by the quantum circuit, then the top left corner is A. The second step is to carefully compose this circuit for A to get an embedding of A square, A to the power 4, and so on up to A to the power T. So for example, let's just look at a quantum circuit that implements this operator. If you just compose this circuit with itself, then the matrix implemented by the composition of those two circuits is not quite going to embed A square. It's going to have A square plus some noisy terms. So we need to do something to make sure that these noisy terms don't interfere with each other. And the way we do that is by embedding it inside a larger space. So you take this quantum circuit. On some part, it acts as an embedding of A. On the other parts, it acts trivially. And similarly, we do this in a different way for the second circuit. And we combine these two circuits so that these noisy terms don't interfere with each other. So somehow carefully composing these circuits and doing some alterations, from an embedding of A, we're able to produce an embedding of A square. So we do this log T times to get an embedding of A to the power T. And finally, it's not too hard to actually recover the entries of A to the T. You have a quantum circuit whose top left corner, for which the operator implemented by the circuit has top left corner A to the T. You can actually use this circuit to recover the entries of A to the power T. So this uses some basic routines like Grover search and so on. So this is what I wanted to say about the quantum log space algorithm for powering contraction matrices.
How large is the final matrix that you would get when you want?
It's polynomially larger. So so if your original matrix was of size 2 to the s by 2 to the s, I think what you'll get is polynomial in T times 2 to the s by 2 to the s or something. So each time you'll
correct.
Each time I think you're, yeah. So yeah, so this is what I wanted to say about this result. I'm not going to talk about PRGs for quantum algorithms that read random bits, but let me just say that this is very similar to the construction of PRGs in the classical setting. And in the classical setting, we use extractors that are resilient to classical side information. And here we're going to use extractors that are resilient to quantum side information. So it's essentially taking the INW generator and modifying the definition so that everything goes through even if your state was a quantum state. For this, we make use of quantum extractors that have been studied by Fer and Schaffner before. So let me conclude. In this talk, we saw a way to differ intermediate measurements for time t spaces algorithms. The first way resulted was a simulation in time t times 2 to the order s and space s plus log t. This result also had connections to the problem of contraction matrix powering. The second result was a simulation that ran in time t poly s and space s log t. And this result had connections to pseudo-random generators for quantum algorithms. So let me conclude with some open questions. The first question is that what is the optimal time-space trade-off that we could hope to achieve? Can we defer intermediate measurements in time polynomial in S and T and space S plus log T? This is in some sense the best that we can hope for. So I'm guessing that this type of result would require techniques that are different from both of the techniques that I mentioned. Another open question is focusing just on the second result. Can we show a similar result for eliminating reset operations? So this would be stronger than the result for eliminating intermediate measurements, but the connection to pseudo-random generators no longer holds. So this might require completely different techniques to show. So this brings me to the end of my talk. Thank you so much for listening. I'm happy to take questions now.
Yeah, Ronald has it. Yeah.
Can I ask a question?
Yeah, hi Ronald.
Can people? Nice talk, Uma. I wanted to ask about the second result on this slide. So if you start with polynomial time and logarithmic space, then you end up with log squared space. And this is very reminiscent of what happens if you apply a Savage's theorem to an algorithm that has non-deterministic log space, because you would end up with deterministic log squared space. Is there a connection here with Savage's theorem and non-determinism?
So one is that the runtime here is polynomial, and Savage's theorem will only give you a runtime of 2 to the log square.
That's right. Yeah, it's much worse.
It's worse. And actually, you can, there is some kind of a Savage's theorem in the sense you can show that all quantum log space can be simulated by classical log square space and 2 to the log square time. So we already had a result where you can use log square space and 2 to the log square time.
I see. Is that this old result by John Watrous?
Yeah.
I see.
Yeah.
Thanks.
Sure.
Jay Kumar has a question.
Hi, Uma. I missed something. In one of your results earlier, you said that something you prove also holds with reset. And then now you say that the thing is, with reset is not possible. I'm getting a little confused.
Yeah, good question. So what I showed holds also with reset is the pseudo-random generator. So if you take an algorithm with reset operations, which also has access to random bits, those random bits can be eliminated. We don't know how to eliminate the resets.
So in the case of an usual measurement, you could have simulated the measurement using random bits, and then you are going to replace the truly random bits with pseudo-random bits.
Exactly.
Yeah, but with the reset, you cannot do, this two-step process, because the reset cannot be replaced by a
random and unitary. Yeah.
Okay, got it.
Yeah.
Thanks.
So you just mentioned that quantum log space is also in log squared space and 2 to the log squared in time, is it?
Yes.
Just like,
yes.
Okay.
So that is essentially because all matrix multiplication problems can be solved in that much space and time. And this is just a unitary matrix multiplication. So in particular, you can use a matrix multiplication algorithm to solve this. Sort of.
Nice, very nice. So are there any more questions? No, I don't see any more questions. So then let's thank Uma for a lovely talk. Thank you.
Thank you.
Thanks, Uma. Great.
Really nice talk, Uma.
Yeah.
Thanks, Alok.
Okay, so maybe just to wind up, so this is the last talk in this series that we had planned. So thank you all for joining, and I hope you will, if you missed some of them, the recordings are up of all the talks, and please go and check them out. And we will plan to have more talks, but not in this kind of dense pack, but maybe once a month or so, to keep up the momentum. And we really do hope that things will permit us to have physical events for the center in the coming months. So maybe after the academic year restarts in August. So let's look forward to that, and see you all either here or there or somewhere. Thank you so much.
Thank you.
Bye.
Bye.
Bye. Bye.